You know that tiny, brilliant flash when you strike a match? It's something we see all the time, but it's absolutely packed with the secrets of chemical energy. So today, let's get into it. We're going to uncover the science behind that spark.
I mean, really think about it for a second. You've got this little stick of wood, you scrape it, and bam, you get this sudden burst of heat and light. It's a tiny, controlled fire, right? But where did all that energy even come from? It wasn't there a second ago, or was it?
So what is that hidden energy? Well, to figure that out, we need to dive into the world of thermochemistry and see what's really going on at a molecular level to unleash all that power.
To understand the spark, we got to back up a little and get a handle on what energy itself even is. And its very core, energy is just the capacity to do work or to supply heat. It's the stuff that makes things happen, from a giant waterfall crashing down to the quiet chemistry inside a battery.
Now, energy basically comes in two main flavors. You've got kinetic energy, that's the energy of motion. Think of the water just thundering over a huge waterfall. But that exact same water, when it's just sitting there, held back by a dam, that's potential energy. It's stored up energy, just waiting, all because of its position.
And this brings us to one of the most fundamental rules of the entire universe. The energy from our match wasn't just created out of thin air. Nope, it was just converted. The potential energy that was stored up in the chemical bonds of the match head was transformed into kinetic energy, the heat and the light that we can actually see and feel.
Okay, so we've been talking about energy in a pretty big picture way, but that flash from the match, well, it felt hot. So what's the deal with heat and temperature? To figure that out, we need to zoom way in, down to the microscopic world of atoms and molecules.
When you get right down to it, temperature is really just a measure of how fast atoms and molecules are zipping around. So in hot water, the molecules are buzzing all over the place with a ton of kinetic energy. But in cold water, they're moving much, much more slowly. It's that simple. Hot means fast, and cold means slow.
And here is a super important distinction. Temperature is a property of an object. It's a measure of its internal jiggling, you could say. But heat, which we symbolize with a Q, isn't something an object has. Heat is the transfer of that energy from a hotter object to a colder one. Heat is energy on the move.
And this flow of energy is totally predictable. So picture this. When two objects at different temperatures touch, the faster, hotter molecules literally bump into the slower, colder ones, and they transfer some of their energy. This keeps happening until all the molecules have the same average kinetic energy. We call that state thermal equilibrium.
All right, so we know heat flows from hot to cold. Now let's apply that idea directly to chemical reactions. Because it turns out chemical reactions can either give off heat to their surroundings or they can pull heat in from them.
Let's look at two perfect opposite examples. An oxyacetylene torch is what we call an exothermic process. It releases a massive amount of heat, so much that it can slice right through steel. But then you have the chemical reaction inside an instant cold pack. That's an endothermic process. It actually absorbs heat from its surroundings, which is exactly why it feels so cold when you put it on your skin.
So let's make this official. An exothermic process releases or exits heat. It feels hot. Because the system is losing energy, we say its heat flow, Q, is negative. On the flip side, an endothermic process absorbs heat, pulling it in. It feels cold. Since the system is gaining energy, its Q is positive.
All right, let's get into the nitty-gritty, the numbers. And this is something you've definitely experienced. You put two different sized pans on the stove. Why in the world does one heat up way faster than the other, even if they're made of the exact same material?
So here's the puzzle. Both of these pans are cast iron. Let's say you want to raise their temperature by 50 degrees. Is it going to take the same amount of heat? The answer is a definite no. And the reason why introduces two really important concepts.
The solution lies in the difference between two key ideas. First, there's heat capacity. This depends on the object's size. The big pan has a bigger heat capacity because there's just more stuff, more atoms to get vibrating. But then there's specific heat. This is a property of the substance itself. The specific heat of the iron in the small pan is identical to the specific heat of the iron in the big pan because, well, it's all just iron. And this is the formula that pulls it all together. The amount of heat transferred, Q, is equal to the specific heat of the substance, C, times its mass, m, times the change in its temperature, which we call delta T. With this little equation, we can actually calculate the energy involved. And hey, this isn't just theory for a science class. These principles are used every single day to measure energy in the real world,
from simple lab experiments to figuring out the nutrition info for the food that we eat.
The science of measuring this heat flow is called calorimetry, and you can do it with a surprisingly simple device. This right here is a coffee cup calorimeter. I'm not kidding. It's basically just 2 styrofoam cups, a lid, and a thermometer. It's designed to trap all the heat from a reaction so we can measure what happens.
The principle behind it is beautifully simple. Any heat that's released by a chemical reaction inside that cup has to be absorbed by the water or solution that's in there with it. So, by measuring the temperature change of the water, we can figure out exactly how much heat the reaction produced or absorbed. Pretty clever, right?
Now for more high-energy reactions, like, say, burning food to figure out its caloric content, scientists use something a little more heavy-duty, a bomb calorimeter. The sample gets placed in a sealed steel container, that's the bomb, which is then submerged in water. They ignite the reaction, and all the heat released is absorbed by the bomb and the water, giving you a super precise energy measure.
And this brings us right back to our daily lives. The nutritional calorie with a capital C that you see on food labels, that's actually a kilocalorie, and its value is determined using bomb calorimetry. As you can see, different types of food pack a different energy punch, with fats being by far the most energy dense.
So, from the simple spark of a match, we've journeyed through the laws of energy, down to the molecular dance of heat, and all the way to the food on your plate. We've seen that energy is never created or destroyed, just converted in reactions that either give heat or take it away. So my question for you is, now that you know the rules, what other hidden reactions are powering your world right now?